Hello students, I am Professor NAVNEET KAUR, Associate Professor in EC Department, SIRT College, Bhopal. Today I will be taking lecture of subject Digital Communication. The topic which I will be discussing here is sampling techniques. In this lecture, I will be discussing the concept of sampling and the different types of sampling. Now, to start with the lecture, first we will study about the sampling. Most of the signals that we use in our daily life are analog in nature. For example, voice signal, weather signals, etc. Digital systems have many advantages in comparison to analog system. For example, they have high noise immunity. They can be stored, processed with more efficient algorithms, more secure system. It is more robust and cost effective. Most of the effective signal processors are digital signal processors, which needs digital information in order to process it. So we need to convert our analog signal to discrete time signal in order to process them through digital signal processor. And at the receiver side, they should be converted back to analog signals so that they can be used by the destination. Sampling is the method to convert a signal from continuous time to discrete time. Now, we will talk about the different types of sampling. There are three sampling methods. The first method is ideal sampling. It is also known as instantaneous sampling or impulse sampling. Here, an impulse at each sampling instant with amplitude equal to or signal at that point of time. Here we can see that we have a train of impulses which are located at an interval of Ts. Ts is the sampling interval. Now to note down from this waveform that here the amplitude of each impulse signal varies according to the amplitude of the message signal. The next sampling method is natural sampling. Here we consider a pulse of short width with varying amplitude. Here we can see that we have train of pulses which are located at an interval of sampling interval Ts, and the amplitude of each pulse varies according to the amplitude of the message signal. Here we can see that the top of the pulses are not flat. Here, the top of the pulses, they change as the message signal varies with time. Now, the next sampling method is flat top sampling. This method makes use of sample and hold circuits. Here, we can see that there is a train of pulses located at an interval of sampling interval Ts, but here, the top of the pulses are flat and they varies according to the amplitude of the message signal. So this is the basic difference between the natural sampling and flat top sampling. In flat top sampling, we have seen that the top of the pulses are flat, though the amplitude of the pulse at the start of the pulse interval varies according to the message signal. But in natural sampling, the top of the pulses are not flat, but they exactly follow the message signal. Now, we will consider all these sampling methods in brief. First, we will consider impulse sampling, which I have told it is also known as instantaneous sampling or ideal sampling. Impulse sampling can be performed by multiplying input signal with impulse train Pt, and it is a periodic signal of period Ts. Here we can see that we have a message signal xt, which is shown here as a sinusoid. When it is multiplied by periodic signal, which is a train of impulses located at an interval of Ts. When we get the product of these two signals, we will get the train of impulses, again which are located at an interval of Ts, but here the amplitude of the impulses is no longer a constant, but it varies according to the amplitude of the message signal. So here we can see an impulse sample signal here in which the top of the impulses varies according to the amplitude of the message signal. We can represent a train of the impulses Pt as summation delta t minus nts, where n is an integer and it is having a value from minus infinity to plus infinity. Now, if I say I'll take n is equal to 0, then I'll get only delta t, which is an impulse which is located at t is equal to 0. Now, if I'll take n is equal to 1, then I'll get delta t minus ts. That means an impulse is shifted to position ts. So we will get an impulse at ts. Now, if I'll consider n is equal to 2, I'll take an impulse at t is equal to 2 ts. Similarly, moving to the negative side of the n, if I'll take n is equal to minus 1, then I'll get delta t plus ts. That means an impulse function is located at t is equal to minus ts. So here in impulse sample signal, the amplitude of the impulse changes with respect to amplitude of the input signal xt. Now, natural sampling. Natural sampling is similar to impulse sampling, but the difference is that here the impulse train is replaced by pulse train of period ts. Now, we can see in this figure that we have a message signal xt, which is getting multiplied by train of pulses. So here we will get a periodic signal which consists of train of pulses located at an interval of ts. After getting a product of these two signals, we will get pulses, but here the amplitude of the pulses varies according to the message signal, and this gives rise to natural sample signal. Now, considering the equation of Pt, which is a train of pulses, I can write it as summation n is equal to minus infinity to plus infinity Pt minus nts. Now, if I'll take n is equal to 0, I'll get a pulse which is located at t is equal to 0. When I'll take n is equal to 1, I'll get a pulse Pt minus ts. That means the pulse is shifted to t is equal to ts. So that's how I get a train of pulses which are located at t is equal to 0, ts, 2ts, or minus ts, minus 2ts, and so on. Now, coming to the mathematical analysis of natural sample signal, here I have told that the natural sample signal is obtained when I'll multiply a message signal xt with train of pulses pt. We know that train of pulses pt is represented by summation n is equal to minus infinity to plus infinity pt minus nts. Now we know that pt is a periodic signal. So any periodic signal can be represented by exponential Fourier series. So here we will represent pt as exponential Fourier series n is equal to minus infinity to plus infinity cn e raised to power jn omega s t. Here Cn is Fourier series coefficient, which is given by the formula 1 upon Ts, where Ts is the period of the signal Pt, and integration between the limits minus Ts by 2 to plus Ts by 2, that is, we will consider the integration over one period Ts. Then Pt e to the power minus Jn omega st, where omega s is 2 pi by Ts. Now, after solving this, we will get this integration as Pn omega s. Here, we will put this value of Cn in equation 2. Here, we have obtained the value of Cn. Now, we will put this value of Cn here in this equation 2. Now, after this value, we will get summation n is equal to minus infinity to plus infinity 1 upon Ts Pn omega s e to the power Jn omega st. Now, since 1 upon Ts is constant and is independent of n, I can take it out of the summation sign. So 1 upon Ts summation Pn omega s e to the power Jn omega st. Now, putting the value of Pt back in equation 1. Here we have seen Pt. Now, the value which we have obtained for Pt, we will put it in this equation 1. So, I'll get xst, which is given by xt into Pt. Now I'll substitute the value of Pt here, which is xt into 1 upon Ts summation Pn omega s e to the power Jn omega s t. Now 1 upon Ts Pn omega s xt I'll take inside the summation xt e to the power Jn omega s t. Now, to get the spectrum of the sample signal, I'll take Fourier transform of both sides because I'll convert the time domain signal into the frequency domain signal. Now, taking the Fourier transform on both the sides of this equation, I'll get Fourier transform of 1 by Ts summation Pn omega s xt e to the power Gan omega st of my right hand side. So 1 upon Ts Pn omega s Fourier transform of xt e to the power Jn omega st, because the Fourier transform will be computed for time dependent signal. Now we know the frequency shifting property that if we have any signal xt which is having a Fourier transform x omega, then if in time domain I'll multiply this xt with e raised to power Jn omega st, then the Fourier transform will also get shifted by omega s. So using this property here, I'll get x omega minus omega s. So looking into this equation, x omega minus omega s multiplied by Pn omega s. So analyzing this equation, we will get that x omega minus omega s, that means the spectrum of the basic signal x omega is repeated after every interval omega s. So here the spectrum which I'll get will be the spectrum of the basic message signal omega s, which is repeated after every frequency interval omega s. So the basic spectrum will be at omega is equal to 0. Then we will get another spectrum which will have omega is equal to omega s. This spectrum will be the replica of the basic message signal spectrum. Then again we will get replica at omega is equal to 2 omega s. And similarly we will get at omega is equal to minus omega s and minus 2 omega s. Now for recovering my message signal, I'll use a low pass filter which will have cutoff frequency plus minus omega m. This low pass filter will pass only the basic signal spectrum and will reject other higher frequency components. So in this way, we will get the message signal at the destination. Now, for recovering or reconstruction of the sample signal, it is necessary that the sampling frequency fs should be greater than 2fm. Or we can consider the sampling frequency at least equal to 2fm. But if we'll have sampling frequency less than 2fm, in that case, the neighboring spectrums will overlap with each other and there will be loss of information. And this effect is known as aliasing. Now, aliasing refers to the phenomenon of a high frequency component in the spectrum of a signal which takes the identity of a lower frequency in the spectrum of its sample version. Here, the time signal cannot be band limited since all signals are time limited. They cannot be band limited. So we get the aliasing effect. For removing the aliasing effect or for minimizing the effect of aliasing, we pass most of the signals through low pass filter before sampling, so that we will get a signal which will have only frequency up to omega s by 2, so that the effect of the overlapping will be reduced. Now, this low pass filter is known as anti-aliasing filter. Distortion will occur when the signal is sampled. And if we will use anti-aliasing filter, the effect of this aliasing will be reduced. Now, this is all for today's lecture. Thank you.